Hi there, I'm Peter Edmunds. I'm head of physics at a secondary school in North London. Thank you to Chat Physics for inviting me along today. I'm going to be talking about towards the holy grail of problem solving, that elusive thing that we are all after. We all want our students to be fluent problem solvers. I'm going to talk about how I approach that today. If you'd like to ask me any questions following this talk on Twitter, you can find me at Edmunds_doctor. Please do let me know if you have any questions. So, first of all, I just want to say I think problem solving is a really admirable aim. I think really it's what we're all after in the classroom. We all want our students to be exceptional physicists who can solve exceptionally hard physics problems. I think that's kind of what we are all looking for here. But what I want to say is that we should not be prioritising this over declarative, factual knowledge. I think that's the wrong approach. I'm going to discuss how actually declarative knowledge is one of the building stones on which problem solving relies. Now I'm going to put up a couple of quotes here which have kind of popped up in recent times to put the kind of like problem in context of what some people think. First quote, do you want a doctor who just knows what they've been told by others? I want a problem solver, someone who can make observations and inferences. We're going to talk about the issues behind this quote today. Frankly, yes, I do want a doctor that knows what they've been told by others because I think that is necessary to be a fluent problem solver. Next quote, there needs to be less rote-style learning and more help for children to develop their own faculty for critical thinking. Again, we're going to talk about how the factual declarative knowledge is necessary for us to develop our critical thinking skills. Knowing more physics does not make a pupil a better physicist. I know a reasonable amount of physics. I think I'm an okay physicist because I know a reasonable amount of physics. I think that is necessary to know physics to be a fluent, to be an exceptional physicist. And we're going to talk about that today. And finally, one final quote from Dan Willingham. Factual knowledge must precede skill. This one I like. I like this one, and we're going to talk about this today. And I'm going to go through one example now with you. So, I'm going to be talking about a few different types of knowledge today, and I'm just going to go through them really quickly. So the first is that I've already talked about declarative knowledge. This is the core knowledge that we need the students to know. This is the factual information that is part of the course, okay? For example, being able to rearrange an equation. I'm also going to talk a little bit about procedural knowledge, i.e. knowing how to do something, knowing how to rearrange equations, and conditional knowledge, so knowing when to do something, going, right, actually, I know when to rearrange this equation, I know when the right situation to do this is. So I'm going to be talking about these three types of knowledge kind of throughout. And I'm going to start off by one example question. This question could probably be a 6-mark question at GCSE. It would be a hard 6-mark question. It's a multi-step calculation, but I'm just going to break down the different parts of knowledge that a student would need to solve a question like this. And if you'd like another example of me going through this, I wrote a blog relatively recently on the role of declarative knowledge in problem solving. So first of all, a tennis ball of mass 50 grams is dropped from a height of 5 meters. Okay, calculate the velocity of the tennis ball when it hits the ground. So the first thing that I would talk about, and the first place that my mind goes to here, is knowing that as an object falls, its gravitational potential energy store reduces and its kinetic energy store increases. So that's the first thing that we need to realise. That's the first bit of declarative factual knowledge. The second bit is, alright, actually, we're given the mass, we're given the height. Okay, there's an equation which relates these in gravitational potential energy. It's m times g times h. Second declarative knowledge, second fact that we need to remember here. And thirdly, the third thing that we need to remember for this question is, alright, on Earth, gravitational field strength is 9.8 newtons per kilogram. So now we've got mass, we've got gravitational field strength, and we've got height. Oh, but wait a second. Mass is given to us in units of grams. Actually, mass has units of kilograms. Oh, okay, that's the next kind of fact, bit of declarative information we need to remember. Oh, okay, also, I remember that to go from grams to kilograms, I need to divide by 1,000. So I'm going to have to divide that 50 by 1,000 to get to 0.05 kilograms, and put that in the equation there. Next, alright, I need to solve this now for gravitational potential energy. And this is the first bit of kind of procedural, conditional knowledge here. Right, I know that I need to put the variables into the equation and calculate the gravitational potential energy. Oh, okay, actually, from declarative knowledge 1, I know that the gravitational potential energy store reduces and it all goes into the kinetic energy store. And so therefore, my equation for kinetic energy is half mv squared. And then next bit of declarative procedural knowledge, we need to put the variables into the equation and rearrange it to find the velocity. So, and then finally, remembering to put our units after the equation, units of velocity in meters per second. So I make that 7 bits of declarative knowledge that we need to know off by heart, and I make that a couple of bits of procedural and conditional knowledge. Now, if you're wondering what the answer to this question is, it's 9.9 meters per second, but my real point is that if you did not know these bits of declarative knowledge, you wouldn't be able to solve this question. And not only that, you might not know how to be able to look up to solve the question, because you might not know, oh right, I have to go via gravitational potential energy to kinetic energy, and you might not get a simple answer from Google trying to find velocity of a ball dropped from a height. And that's especially true as the complexity of our problems increases. So we cannot solve this problem without knowing these different bits of declarative knowledge, and we might not even be able to look up how to do the problem. So it would be extraordinarily inefficient if we didn't know these different bits of declarative knowledge here. Okay, so that's all well and good. We've talked about the role of declarative knowledge in problem solving here. So how can we and how do I prepare students for problem solving? Well, I have a kind of few things going on. The first thing is, as I've just talked about, I absolutely prioritise the declarative knowledge. Okay, and I'm going to talk about a few ways of doing this. I'm going to talk about retrieval in do nows, self-quizzing sheets, those types of things. I'm going to talk about embedding procedural and conditional knowledge into the curriculum and how I achieve this using my ramped worksheets. And I'm going to talk about deliberate practice, SLOP. Practice makes perfect, practice makes permanent. And then finally, how do we feed back to the students when they give us a piece of work or an assessment or something like that. Okay, so the first thing is, as I said, I absolutely prioritise the declarative knowledge. Now this is one of my self-quizzing sheets that I use and give to students. Adam Boxer has a great blog here on core questions at Key Stage 3 level. The way that I've made these is I've kind of broken down the curriculum into what I describe as key learning questions, okay? Those key learning questions are the absolute non-negotiable things that I need students to remember. You have to know all of these. There's no other way about it. You have to know them. So to get there, I encourage the students to self-quiz. I might even give them a test, 10 random questions on this sheet, or maybe 40 random questions over a few of these topics, and they'll be like, but sir, you're telling us the answers to the test. I'm like, good. That's the point. That's what revision is. Okay, you're revising what we have learned. So it's kind of a neat way of tricking them into actually revising what you want them to know. And we can also assess this knowledge remotely, of course, because we're remote at the moment. Quizzical is a wonderful site where I actually have a Twitter video on how to use Quizzical and how to use it to generate Google Forms so that we can do this remotely. Lots of contributors on EduTwitter have submitted their retrieval roulettes there, and Carousel, which Adam Boxer has made, is an alternative as well. Similarly, lots of community contributors retrieval roulettes. And of course, more time-intensive way, we can actually do this ourselves and make our own Google Microsoft form and go from there. So number one thing, let's prioritise our declarative knowledge. Now, this is an example of how I kind of build a class culture of retrieval. This is one of my do nows. You can see it's separated into 4 different sections: last lesson, last term, last year, as well as a harder stretch and challenge question. And you can see that, right, last lesson I've done generators, so I've done alternators and dynamos. Last term, recapping some waves knowledge. Last year, I'm recapping some energy knowledge. So this is a really nice way. The research shows that kind of the longer the spacing gap on retrieval, the more effective it is of embedding retrieval into our lessons and curriculum and creating a class culture of it. Okay. So the next thing that I'm going to talk about is procedural and conditional knowledge. Now, ideally, this should be embedded throughout your curriculum. So, for example, knowing to rearrange equations and knowing how to rearrange equations should be embedded throughout in any lesson when you introduce equations. So this is an example, one of my worksheets for a wave equation, and you can see here that I've made it clear to the students why certain questions are harder. So I've said, right, the medium ones, you need to rearrange the equations. So that's the thing that you need to practice for that. That's the procedural and conditional knowledge that you need to practice here. Hard, alright, I'm putting in unit conversions, a different bit of procedural and conditional knowledge here, and we're going to practice it fluently. And if we do it throughout the year, then students are going to get really, really good at it, okay? And that in another way is kind of retrieving it throughout. So ramped worksheets is how I embed different bits of procedural and conditional knowledge into my curriculum. And thirdly, practice makes perfect, practice makes permanent, deliberate practice, slop, as it's commonly called. So the more we practice something, the better we get at it. And if I've embedded my procedural and my conditional knowledge, and if I regularly review it, we've got Ebbinghaus's famous forgetting curve here, the more we review it, the longer, if I put my physics hat on, the half-life of remembering our content is, where Ebbinghaus got some people to remember some completely made-up syllables and then tested them at different intervals with how much they remember. And you can see that the half-life of how long we're remembering that is kind of extended. Now, the more often we repeat something, the longer we remember it for. So we're really, really practicing both declarative and procedural and conditional knowledge to make sure that students are remembering it as long as possible. And just one thing I want to note is that the very best problem solvers have seen similar problems before. Okay? Now, what do I mean by that? I spent 4 years doing my PhD. If I were to do my PhD now, I would probably do it in about 6 months, the actual experiments and things like that, okay? So the knowledge is kind of predictable. Our domains are predictable. We can kind of, when we see certain problems, we can relate it to similar other ones, okay? So if we've practiced similar problems before, that's the best way to get to become a fluent problem solver, is by actually seeing similar things come up before. And then finally, I'm going to talk about feedback. All of what I'm about to talk about is in Adam Bloxer's blog here, what to do after a mock assessment. I'm going to extend that so it's not only an assessment, but it could be an assignment, a piece of work or something like that. So of course, if they do a bit of work, it's important that we offer some feedback in some way. Now, this blog has kind of changed my mindset with how I go over, kind of give feedback to the class. So I used to just go over the answers, and I'd talk about the answers and I'd maybe just work them through on the board. But I no longer just do that, because if a student's done really badly and they tried really hard, they're going to be really upset and demotivated. Oh, I tried really hard on this and I'm really disappointed. I'm actually demotivated for the rest of the lesson. Or they could be focused on finding a way to scrounge another mark. So that's exactly what I wrote. Can I get a mark for this? Can you read what I said? I want another mark for this. Or if they've absolutely smashed it, they can be so smug about their score that they don't feel the need to pay attention. I got 90%. I got this question right. I'm going to switch off. I don't need to listen. I've mastered this. I've got this. So I no longer just go over the answers. Instead, what I do, and still from this Adam Boxer blog here, before giving the work back, I reteach some things. So I go, right, okay, actually this came up as a theme in the class. This thing we didn't do very well. So because we didn't do very well at it, I'm going to reteach it. And then I reteach it, and then I'll give them a question similar to it, and I'll give them an opportunity in the future in my retrieval do nows and things like that to come back to it again, extending the amount of time that they remember the information for. And for future classes, if I've noticed that a really big misconception or difficulty has arisen, then I'm actually going to edit my lessons for next year, maybe edit my scheme of learning so that I can address that earlier. Okay, so that's what I do instead, and this is how I implement it. So this question here, explain how the properties of alpha, beta and gamma radiation affect the level of hazard at different distances. Last year, my year 11s, a lot of them were like, oh, gamma radiation, it isn't ionizing, so therefore it's not as dangerous. But no, that's not the case. Right, let me reteach this. All types of radiation are dangerous, but they have different dangers at different distances. So I'll reteach, I'll give some teacher exposition for maybe 5-10 minutes. I'll question to check for understanding. Alright, here's a similar question. Sam and Chris are arguing about alpha and gamma radiation. Sam says that alpha radiation is more dangerous. Explain. Okay, so I get them to practice a very similar question, and I might come back to it in a few days' time so that we can revisit it in that way. Okay, so if they do something badly, I reteach it, I give them some similar work on it, and then I come back to it in the future. Okay, that's all I really wanted to talk about today. If you want to tweet about it on Twitter, find me at Edmunds_doctor, remembering the hashtag #ChatPhysicsLive. Many of the resources that I talked about today are on my site, sciencedoctor.school.blog, and apologies for the self-promotion here, but I have an equations practice pack coming out with Collins soon. It contains lots of deliberate practice, lots of slops, self-quizzing sheets, retrieval practice, kind of embedded throughout. I'm really excited about it coming out, and I hope that it will be useful to you. Thanks for listening, and yeah, any questions, ask on Twitter.